Okay, let's talk about Rolle's theorem and the mean value theorem. Rolle's theorem and the mean value theorem. These both are called existence theorems. It tells you a value exists. It doesn't tell you necessarily how to find the value, but it says what you're looking for is there. Keep looking for it. These two theorems are not necessarily very useful for applications. It's not like we're going to do word problems later that use Rolle's theorem and mean value theorem, but rather they are used in advanced calculus to prove everything else. The mean value theorem is used to prove the fundamental theorem of calculus, which we haven't even talked about yet. So we don't need to spend more than a day on this section. It's not particularly difficult, but you just need to understand that they are fundamental theorems that are used to prove other theorems in calculus. So what do they say? Rolle's theorem says let f be continuous on a closed interval from a to b. And by the way, I uploaded this handout yesterday. I'm all about not carrying a big thick book when I can. So I uploaded this yesterday. If you didn't print it this morning, that's okay. These two theorems are straight out of the book. Rolle's theorem is on page 10. All right, I interrupted myself. Let f be continuous on the closed interval from a to b. Closed interval means including the endpoints, and that's what those brackets represent. And differentiable on the open interval from a to b. Open interval means not including the endpoints, and that's what the parentheses represent. Remember, in order to be differentiable at a point, both the left-hand derivative and the right-hand derivative have to exist. By using an open interval rather than a closed interval, that's saying don't worry about the derivative from the left as x approaches a, and don't worry about the derivative as from the right as x approaches b. We don't have to be differentiable at the endpoints, just everywhere in between those endpoints. If f of a equals f of b, then there's at least one number c in the interval from a to b such that f prime of c equals 0. Now what does f prime of c being 0 tell us? It's a maximum or minimum value. Yeah, I was trying to think. The math teacher brain in me goes, is that always true? Is that always true? Yeah, as long as the function is defined at c, then if f prime of c is 0, there is at least one maximum or minimum value in between a and b. It doesn't tell you how to find it, but it tells you that there is one. So when we use this theorem, we have to make sure that the conditions are met. When you use any theorem, you have to show that the conditions are met. So we want to know, and we can tell by looking at the graph, or some functions we just know are continuous everywhere, like sine or like a polynomial function. But we want to know that the function is continuous on the closed interval from a to b, and it's differentiable on the open interval from a to b. The function may not be differentiable everywhere, but we're going to be given an interval, and if it's differentiable on that open interval, then the conditions are met. Also, f of a has to equal a f of b. That means at its endpoints you get the same y value. Now, if you think about a geometric interpretation of that, it actually makes perfect sense. You wonder who got a Nobel Prize for thinking of it? I guess Rolle's did. That's why it's named Rolle's theorem. If a function is continuous and differentiable on a closed interval from a to b, and f of a equals f of b, how else could you get from here to here without there being at least one place in between where the derivative is 0? If you go up, then to get back to here, you're going to have to come down. So you're going to have a place where the derivative is 0. Or if you go down, you're going to have to come back up, and there's a place where the derivative is 0. So really, Rolle's theorem makes sense. Proving something that is obvious is much more difficult than it would seem. I mean, to us, we just go, duh. Rolle's couldn't do that. Rolle's had to prove it to get his name, get a theorem named after him in calculus. Let me look at a few examples with you. Number 8. This is page 214. Number 8 says find the x-intercepts of the function and show that f prime of x is 0 at some point between the two x-intercepts. So we're given the function negative 3x times the square root of x plus 1. And the first thing we're told to do is find the x-intercepts. How do we find x-intercepts? Okay, if I told you you couldn't use pronouns in a math class, what exactly are you setting equal to 0? The function, not the derivative. To find the x-intercepts, you're setting the function equal to 0. So negative 3x times square root of x plus 1, what makes that 0? Zero definitely would make this 0, and 0 times square root of 1 is 0, so definitely 0. Anything else? Negative 1, because negative 1 would make this factor equal to 0, and it wouldn't matter what that factor was. So 0 and negative 1 are our two x-intercepts. Then we're asked to show that there's at least one point in that interval from 0 to 1 where the derivative equals 0. So it's time to find the derivative. Go for it. You have the same thing I do by the product rule? All right, let's talk about factoring out fractional exponents. The coefficient of that first term is negative 3/2. So what could you factor out so that your answer would not be left a complex fraction? You could factor out the negative 3/2, or you could just factor out the 1/2. I'd go ahead and factor out the negative 3/2 because you can get a negative 3 from both terms. So I would factor out a coefficient of negative 3/2, and what else? X plus 1 to the lowest exponent. All right, that's my GCF. What would I have to multiply times that GCF to get back that first term from the product rule? It just needs x. I got the negative 3/2. I got the x plus 1 to the negative 1/2. So just x. If I factor, be really careful here. Whatever you write down, just check it. What do you multiply times negative 3/2 to get negative 3? All right, if you try a positive 2, then does negative 3/2 times positive 2 give you negative 3? Yeah, the 2's cancel and leave you the negative 3. And then you have x plus 1 to what power? First, because negative 1 plus 1 gives you back this 1/2 that you started with. So when I write that as a single fraction, factored as completely as possible, I'm going to have -3 in the numerator, 2 in the denominator, square root of x plus 1 in the denominator, and then in the numerator, I'll have whatever inside brackets cleans up to be. That would be 2x plus 1x is 3x, and then 2 times 1 is 2. All right, what are the critical numbers for the derivative? -1. In order to be a critical number, the original function has to be defined there. Is the original function defined at -1? Can't take the square root of 0? I can take the square root of 0. So -1, the function's defined, but the derivative is not. That makes -1 a critical value. We're actually not looking for critical values here. We're just looking for the original direction said show that there's something that makes the derivative 0 in between its intercepts. So what's the number that makes the derivative 0 and is between 0 and -1? -2/3. What we do on any given problem depends on what we're asked to do. And what we're asked to do here is show that there's one number, or at least one number, between the x-intercepts that makes the derivative 0, and we found it, so we're true. Number 12 has a little bit different instructions, but it's a polynomial. And we're given a closed interval from -2 to 4. Here's what we're asked to do. Determine whether Rolle's theorem can be applied to the function on the closed interval given. This closed interval is -2 to 4. If Rolle's theorem can be applied, find all values of c in the open interval from a to b such that the derivative is 0. If Rolle's theorem cannot be applied, explain why not. Basically, there are 3 conditions that have to be met in order for Rolle's theorem to apply. The function has to be continuous on the closed interval. It has to be differentiable on the open interval, and f of a has to equal f of b. In other words, at its endpoints, you get the same y value. What do you know about the continuity of a polynomial function? Polynomial functions have no hole skips or gaps. It's continuous everywhere. Specifically, it's continuous on the closed interval from -2 to 4. What do you know about the differentiability of a polynomial function? It's differentiable everywhere. It doesn't have any discontinuities. It doesn't have any vertical tangent lines. So it's continuous and differentiable. On all real numbers. That's the first 2 conditions. It's continuous and differentiable, not just on -2 to 4, but everywhere. What's the third condition? At its endpoints, we have to get the same y values. So we need to find f of -2, and we find f of 4, and see if they give us the same y values. F of -2 would be negative 6 times 0, 0. What about f of 4? Is also 0. The first thing we were asked to do is tell whether or not Rolle's theorem applies. All three conditions are met, and therefore Rolle's theorem applies. The last thing we were asked to do is, if it does apply, find that value c somewhere on the open interval from -2 to 4, which makes the derivative 0. Now, if we leave the function like that, what's it going to take to find the derivative? It's going to take the product rule and then the chain rule within the product rule. That's absolutely fine. We could do that. Just to save us a minute of time, I went ahead and multiplied it out. I'm just going to tell you what I got. Make it easier for you to differentiate. That's from just multiplying x plus 2 times x plus 2 times x minus 4, which I figured would be just as easy as using the product rule. So find the derivative and find what makes it 0. What numbers make the derivative equal 0? -2 and 2. But look back at the theorem just a second. It says there is at least one number c in the open interval from a to b. The open interval a to b doesn't include the endpoints. So is -2 in the open interval from -2 to 4? No. Not in that open interval. So the value of c that we're looking for is just the +2. Rolle's theorem guaranteed us that there would be at least one point on that open interval where the derivative equals 0, and we found it. It's 2. All right. There must be something different in 14 and 16, or I probably wouldn't do any more examples. Same directions. Tell whether Rolle's theorem applies or not. If it doesn't, tell why it doesn't. If it does, find the guaranteed value of c. What if I go ahead and tell you that Rolle's theorem doesn't apply here? Can you tell me why? What about absolute value? Rolle's theorem doesn't say anything about it. Oh, it's not differentiable at sharp turning points. And where does this graph have a sharp turning point? At 3. If you asked me if it was differentiable on the interval from 4 to 10, would it be differentiable on the interval from 4 to 10? Yeah, but if you ask me, is it differentiable on the interval from 0 to 6, that includes that sharp turning point. And so, no, Rolle's theorem does not apply. because f of x is not differentiable at x equals 3. And that's all you have to say. One more, number 16. What can you tell me about Rolle's theorem as it applies to that function on the interval from -1 to 1? Yes, sir. Why?
Because it's not continuous throughout the entire closed interval.
And where specifically is it not continuous? Yeah. It's discontinuous wherever the function's undefined. It's undefined, whatever makes the denominator 0. As long as that is on this interval for which continuity is required, then the theorem just doesn't apply. If you gave me a different interval that didn't include 0, then maybe Rolle's theorem would apply. We would still have to check differentiability. But the only problem here is that 0, the only point where the function is discontinuous, is in that interval for which we have to have required continuity. It's not. All right. One more problem using Rolle's theorem, and then we will get to the mean value theorem. 24, not 23. 24. Here are the instructions. Use a graphing utility to graph the function on the closed interval from a to b. Determine whether Rolle's theorem can be applied to the function on that interval, and if so, find the value of c in the open interval from a to b such that f prime of c is 0. So let's graph it. It is x minus x to the 1/3. I don't remember the window that I used when I graphed something on this calculator. So I'm going to go zoom, and number 6, zoom standard sets it back to the default -10 to 10. That's what the graph looks like from -10 to 10 on both the x and y axes. What interval are we really concerned about? 0 to 1? The function has to be continuous on the closed interval and differentiable on the open interval from 0 to 1. So I'm just going to zoom in on that. I don't know why I prefer changing the window than using zoom and n. You can do either one, but I'm just going to set my window from 0 to, from 0 to 10, and that wasn't 0. Try again. 0 to 10, counting by ones. My y's were so close to the x-axis that I want to choose really small y's. I'm going to choose maybe, well, what if we just go from -1 to 1, counting by tenths. And I keep getting this little preview of what my graph is going to look like. The only other thing I want to change to have a better picture, I think I want to see what's going on immediately to the left of that. I'm going to change those x's to -1 to 10. Or -1 to 2, doesn't matter. -1 to 2. That's the window I'm going to use. Here's the graph. Does the graph look continuous from on the open interval from 0 to 1? Yeah. Really, without looking at the graph, we know that that function would not have any holes, skips, or gaps. It's definitely continuous from 0 to 1. What about differentiable? What are the 3 things that we know cause non-differentiability? Sharp turning points, vertical tangent lines, and I forgot about that one. That makes 4, Christina. Wild oscillations between 2 numbers, and the other one I was thinking about was discontinuities. So, does it look like any one of those things is going on the interval from 0 to 1? That's a vertical tangent line right there. So it's continuous everywhere, but it has a vertical tangent line at 0. It's not differentiable at 0. Yeah, I've got to think about that just a second. Yeah, it's continuous on the closed interval. Oops, you can't see what I'm writing. It's continuous on the closed interval. There is a point where it's not differentiable, but that point's not on the open interval from 0 to 1. It's not differentiable at 0, but that's not a problem. And so the only other condition that we have to ensure is met is what? What's the other? F of A has to be the same as F of B. So what is F of 0? 0. What's F of 1? 0. So Rolle's theorem applies. And if Rolle's theorem applies, then we're supposed to find that guaranteed value of C. What's that guaranteed value of C? I don't mean what's the answer, I mean what is it that we're looking for? Looking for what makes the derivative 0. So the derivative would be 1 minus 1/3 x to the negative 2/3. And we're looking for what makes that equal 0. You could either get a single fraction and see what makes the numerator 0, or You could add 1/3 x to the negative 2/3 to both sides. And then multiply both sides by 3. I guess in the same step, I could have multiplied both sides by x to the 2/3. And then what? I'm solving for x. What would I do next? Divide by 3. And then what? This means the cube root of x squared. How do I something to the 2/3? Raise it to the 3/2. Raise both sides to the 3/2. And then how can you write 1/3 to the 3/2 as simply as possible? I mean, 1/3 to the 3/2 would be okay as an answer. Or I could get a decimal approximation and that would be okay as an answer. But I think the simplest way I could write it is if I went ahead and cubed the 1/3, I'd have 1/27 and then took the square root of that. So it's 1 over square root of 27. And then simplify that as much as you want or as much as you have to. Since 27 is 9 times 3, you could take the square root of the 9 and just leave the 3 under. Check and see if that's the answer in the back of the book. If that's not the answer in the back of the book, then rationalize the denominator. I actually don't know what the easiest way to solve that problem would have been. It may have been right here, go ahead and get a common denominator, then you'd have a single fraction and set the numerator equal to 0. I don't know if that would have been any easier or not, but solving equations is something I should be really good at by now. All right, any questions? That's Rolle's theorem. What about the mean value theorem? It has nothing to do with personality disorders. It's not that kind of mean. Rolle's theorem is used to prove the mean value theorem, and the mean value theorem is used to prove the fundamental theorem of calculus. So even though we're not really going to use Rolle's value theorem and mean value theorem for anything else this semester, you should know them. You should know basically what they say because they're used to prove something called the fundamental theorem of calculus. That has to be big. You know, it's almost the end of the semester. Well, it's almost the end of the semester now, but we've got a ways to go before we talk about the fundamental theorem of calculus. All right, the mean value theorem has the same beginning conditions. The function has to be continuous on a closed interval from A to B, and it has to be differentiable on an open interval from A to B. And those are the only two requirements. If those two things are true, then there is some number C in between A and B such that f prime of C equals f of B minus f of A over B minus A. What does that look like? There's no limit in there. You put the limit in there, you get the derivative. This is just the difference in 2 y's over the difference of 2 x's. That's just what? That's just slope. That's the slope of the line through the point, actually slope of the secant line, because this may not be a linear equation, but it's the slope of the secant line from the points A, comma, f of A, B, comma, f of B. These two ordered pairs, if I told you to find the slope of the secant line between those two ordered pairs, that's what you would use to find the slope of the secant line. And the derivative gives you the slope of the tangent line. So all the mean value theorem says is when these two conditions are met, there's some point where the slope of the secant line gives you the same thing as the slope of the tangent line. Or there's some point where the secant line and the tangent line are parallel. Doesn't seem big, but it must be big if it's used to prove the fundamental theorem of calculus. All right, so let's do last two problems real quickly. Number 42. Says in exercises 39 to 52, determine whether the mean value theorem applies. That means check the differentiability and the continuity. If the mean value theorem can be applied, find those values C, where the slope of the secant line is the same as the slope of the tangent line. All right. So 42. Thank goodness it's a nice little polynomial. Are the two conditions for the mean value theorem met? What are the two conditions? Continuous on the closed interval, that's continuous everywhere. Differentiable on the open interval, that's differentiable everywhere. So mean value theorem applies. Continuous and differentiable on all real numbers, so the mean value theorem applies. So how do we find that point where the slope of the secant line is the same as the slope of the tangent line? Find the slope of the tangent line. Find the slope of the secant line, set them equal to each other. All right, so eeny, meeny, miny, mo. Let's do the slope of the secant line. Let me think just a second. We're looking for the point C in the interval from A to B. So I'm cheating for a second. Okay, I forgot what I was doing for a second. What am I doing? Hold on a second. I've lost my whole train of thought. On the interval from A to B, so we want to find f of 0 is A, B is 2. We want to find f of 2 minus f of 0 over 2 minus 0. Sorry, I lost my train of thought for a second. Slope of the secant line from, here's what was bugging me. 0 and 2 are giving me, are the x values, and I want the y values to plug into that formula. So f of 2, if I let x be 2, then I have 16 minus 16 is 0. And also if I let x be 0, I get y is 0. So the slope of the secant line between the points 0, 0 and 2, 0 is just 0. And the slope of the tangent line we get that from the derivative. And we're looking for where the slope of the tangent line equals the slope of the secant line. So we're looking for what makes the derivative 0. If the slope of the secant line had been something else, if it had been 2, for example, we'd be looking for what makes that equal 2. But because it's 0, we're looking for what makes the derivative 0. And that's pretty easy on this one. That's the value of C we were looking for, cube root of 2. All right, most of what we have done is has been polynomials or algebraic functions. Let me see, 44 is as well. It's not bad. The functions f of x equals x plus 1 over x. We want to see if the mean value theorem applies on a closed interval from -1 to 2. And Glenn's already saying no. Why, Glenn? It's not continuous at 0, and 0's in that interval, which requires continuity. So we can say mean value theorem does not apply because f of x is discontinuous at x equals 0. Give me a different interval and the mean value theorem may apply. As long as that interval doesn't include 0, it probably does apply. But if you include the 0 in your interval, then the mean value theorem doesn't apply, so you don't have to find that value of C. All right. Hey, it's been a while since we finished 5 minutes early. It's been a long time.